Today we started Eureka Pilot with Lesson 7 called Bacteria and Exponential Growth. There's basically two major things you need to be able to do from this section. And the first is to be able to solve for an exponent by hand if its answer is a whole number. The opening exercise is an example of this. So in number 1, or in letter A, we have 2 to the x equals 2 to the third. So we can recognize that the 2 to the x and the 2 to the third have the same base. Therefore, I can just set my exponents equal to each other, and I get x equals 3. When we get to an example like part B, we see they both have the same base. The right-hand side doesn't have an exponent. By default, I know that's 1 because 2 to the first is 2, so x equals 1. Now, letter C gets a little more complicated. It has 2 to the x equals 16. So we could, in this one, just be thinking about 2 to what power is 16. Hopefully we know that off the top of our head, but you are always welcome to go through and say 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, not sure why my pen switched colors, 2 cubed is 8, 2 to the 4th is 16, and so on and so forth. So if we use that process, we can then see that it's when the exponent is 4 that 2 to the 4th is 16. Now, one option that's going to come in handy in just a little bit is that we could have said, okay, 2 to the x equals 16. I could rewrite 16 as 2 to the 4th. Again, this part is not a skill you necessarily needed for this problem, but we'll use it in just a few minutes. Letter D and E add another twist because it's equal to 0 and there's more going on. So in one like D, you would just want to add 64 to both sides first. Get 2 to the x equals 64. Again, ask yourself x to what power is, or 2 to what power is 64, and it's when x equals 6. Again, I could think about it like that, or I could rewrite it as 2 to the x equals 2 to the 6th first. Get it to that situation where we have the same base and can set the exponents equal to each other. Letter E, I'll just do quick. 2 to the x equals 1. You'll recall from last chapter that anything to the 0 power is 1, so therefore x is 0. Now letter F is where it comes in that this star up here, that'll star again, rewriting the answer as 2 to some power is going to be helpful. Because in letter F, when I have 2 to the 3x equals 64, if I can make it so that 2 to the 3x equals 2 to some power, so 64 we've already reviewed is 2 to the 6th power. If I can rewrite it like that, then we can follow the situation in example 1 and all of these where the two bases are the same. Therefore, I can conclude that those exponents must be equal to each other. Now this one looks a little different because it's an algebraic expression, but now I can just divide both sides by 3 and I get x equals 2. So the strategy of knowing that you can change a number into a base to some power allows us to use this strategy of then setting the exponents equal to each other. So finally, letter G, I have 2 to the x plus 1. 32 I know is 2 to the 5th. Again, same base, so I'm going to say then I know x plus 1 has to equal 5. And now I can solve that for x. Get x equals 4. Okay. Again, I said the first strategy, or the first thing that you'd have to be able to do is to be able to solve for those exponents, but in these very simplistic situations where we're getting a whole number as our answer every single time. And the strategy for doing that is to get both sides to have the same base, 2 exponents, because then you can set the exponents equal to each other. The second thing we talked about today is what happens if it's not a nice, neat number. So we're going to switch ahead to this example, which I'll let you read on your own, the background of it. But basically, if we look at this, we're going to say we have a bacteria colony that starts with 1 bacteria, and the population of bacteria doubles every day. That's actually a review of what we've done already, where I could write an equation. P of t equals, the initial amount is 1, times, it doubles every day, so the rate of change is 2, and then to the t power. So that's my function that I can use to model that bacteria. And then what we could do is build a table for it. So after 1 day, after 2 days, after 3 days, after 4 days, after 5 days, I plug in 1. Well, 2 to the first is 2. 2 squared is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32. So really we're kind of looking at what we've already talked about a little bit. But now we're going to take it to a little bit different level. So let's talk about using this table. How many days will it take for the bacteria to reach 8? Well, I look at my table, I find the bacteria is 8 when it's day 3, so it takes 3 days. The next question is very similar, but now we want to know how long it takes to reach 16. Well, again, I find the 16, and that's going to take 4 days. Again, if those were specific questions, I could do those without a calculator and get a very exact answer. It's when we get to questions like this next one that we run into a problem. It says, roughly how long will it take for the population to reach 10? The problem is that I look at my P of T column and I never get 10 as an exact answer, which should make sense because 2 to the T, when does that equal 10? Well, I can't rewrite 10 as 2 to any power as a whole number. So I have to look at this table, and what I can see is that it happens between these two situations, between 3 days and 4 days. So I can't be specific right now, but I could say between 3 and 4 days by using that table. So the second thing we're going to want to be able to do from this section is be able to do a problem like this and get as close to accurate as we can. The first step to that is going to be able to figure out the two integers that it's between. So just like we did, if we want to know how long it takes to reach 10 days by using this table, I can see that it's between 3 and 4 days. Once I have that, I can then take it one step further. I know it has to have a decimal answer. So I could ask myself, well, what if it was 3.1 days? I always start with the lower value of my two end caps, and I would type that in. So I would literally, in my calculator, I would need a calculator for this, do 2 to the 3.1. And I got 8.574. Still not close to 10, so I do 3.2. So I kind of work my way up, increasing that first decimal place by 1 every time, 9.190. So that was 2 to the 3.2. 2 to the 3.3, I get 9.849. And now 3 to the 4, I actually surpass 10 and get 10.556. What this means is that originally I said, okay, I know it's going to be between 3 and 4 days, but now I can say that is actually going to be between 3.3 and 3.4 days because 10 falls right between those answers. So I'd be a little more accurate. Now, when we give you problems like these, we will tell you how many decimal places to go to, and this is the strategy you would use. If we say 1 decimal place, you'd be done. You'd say between 3.3 and 3.4 days, or you could answer about 3.3 days. Usually we'll ask you to go to at least 2 decimal places, so if you turn your page over, you'll see a couple more tables. And this next table I'm going to use to do the next part. Now remember, we said it's between 3.3 and 3.4. So now if I want to go to 2 decimal places, so 2 decimals, I'm going to take that lower value, 3.3, and I'm going to add a decimal place. So naturally it's strategic to start at 1. You could jump around if you really wanted to. So again, I would do 2 to the 3.31. When I do that, I get 9.918. I'm getting closer to 10, but I keep going. I always check the next one. So you'll see that I'm always increasing my last decimal place by 1. When I do 2 to the 3.32, I get 9.987, getting very close to 10. And then I would check 3.33. So 2 to the 3.33, and I get 10.056. And again, we're always looking for this point where we find the point where 10 falls between. And so I would say that if I needed 2 decimal places, it would be between 3.32 and 3.3 days. So after about 3.32 days. So again, if the direction said to use 2 decimal places, I'd stop there. If I asked you to go as far to find 3 decimal places, you would continue. Again, I would take the 3.32, the lower end of what I just found, add another decimal place, and I always start at 1 for strategic purposes. So I would do 2 to the 3.321, I get 9.994, and then I would do 3.322, again just changing that last decimal place, and I get 10.001. So as I can see, for 3 decimal places, the most accurate answer I could come up with is that it's somewhere between 3.321 and 3.322 decimals. Obviously, if you want to go to 5 decimal places, you just complete this process, or continue this process to 4 decimal places and then to 5. So those are the 2 major things you'll have to be able to do. Last but not least, if you go ahead to the next one, we could give it to you in just this format where I just say 2 to what power is 1,000 to 2 decimal places. Again, I would follow that same strategy even if I don't have a table. First, I find that it's between 9 and 10. So then I start doing 9.1, 9.2, 9.3, and I get that it's between 9.9. And then I keep going, and I figure out that at about 9.97. Okay, so again, it's kind of a guess and check model, but with a strategic plan to be successful. Thanks a lot, and tomorrow we will work on lesson 8.